about interacting QFT on causal sets.
Hello, hi everyone. I'm Emma Albertini. I'm a PhD student in Imperial. I want to thank the organizer for giving me the opportunity to introduce to you to this framework that I've been developing with my collaborators in Imperial, Professor Feridoker, Arad Naziri, and Stav Zalel. And I'm currently working in RRI here in Bangalore for a few months to continue working on this topic. I try to be I just try to bring to you a brief idea of what causal sets are, because I know that most of the audience probably is not familiar with the theory. And then I'm going to introduce you to the free theory and the interacting theory that I've been developing with my collaborators. So what are causal sets? Causal set is a partially ordered set which is locally finite. And the idea is that the set represents space-time points. And we are imposing on this set a partial order which respects certain properties, which are reflexivity, acyclicity, transitivity, and locally finiteness. There is a theorem in the 60s, 70s by Ellis, Woking, and Malament, which states that a Lorentzian geometry is described by a metric which has 10 degrees of freedom. And of these 10 degrees of freedom, 9 of them are encoded into the causal order. So the missing degrees of freedom is the volume element. That usually in the continuum, people just take the determinant, like our usual notion of volume element as the square root of the determinant of the metric. However, we go a bit forward, and what we think is that instead of using this notion, we are just going to discretize the spacetime, and counting the number of elements is going to tell us the volume element that we are considering. So our motto is that just thanks to the causal order and the discretization, so the number of elements, we can recover the same information as a continuum Lorentzian geometry. Here, just going to give you a brief example of what a causal set is. It is a 5-element set where then I'm imposing some partial relations, some partial orders. And we can represent our causal set through a directed graph or an essay diagram where I'm representing all the causal relations between the elements. And there are two key objects, the causal matrix and the link matrix. So in the causal matrix, the entries are 1 where 2 elements are related. In the link matrix, instead, the elements are 1 if the entries are 1 if 2 elements are nearest neighbors. With that, I mean that, for instance, the nearest neighbors of 1 are just 3 and 2. Instead, 5 is not a nearest neighbor of 1, since there is the element 3 that connects the 2 as well. Now, given a continuum manifold, you might wonder, how do we discretize this spacetime? And we don't do it through a lattice, because this would break Lorentz covariance, and we really want to keep Lorentz covariance. So what we do is that we choose the points according to a Poisson distribution. And since we are just using the volume measure in this computation, this process is completely Lorentz invariance, and so we are not picking any specific frame through our discretization. And in this way, the average number of points per unit volume now corresponds to the density that we choose, through which we do this procedure of discretization that we call sprinkling in technical terms. So now we have this discrete setup. We don't have any tangent space. How do we build a dynamics for a scalar field, for instance? So we decided to start from a more algebraic QFT perspective and start from a retarded propagator. And we define the retarded propagator depending on which spacetime we're working on, using a open stop model. So we just look at the trajectory between 2 points, and we try to weight the different paths that can be taken between point X and point Y, depending on, and we choose the weights so that then our results can match with the continuum propagators. Here is an example in the 2D case where now the retarded propagator in flat spacetime depends just on the causal matrix and the mass parameter for our massive scalar field. And I'm comparing the results that we get for time like separated points of the retarded propagator in the continuum in real space, of course, with the red line, and then the results that we get from causal set simulations. Now, given a retarded propagator, we need to impose some commutation relations, and we impose the Pierce bracket between two fields at different space-time points. And imposing the commutation relations imposes causal relations, which gets automatically satisfied from our definition of the retarded propagator, so that if 2 points are space-like, the commutator vanishes. What's really nice about the results of our commutation relation, which we call a poly-Jordan function, is that this poly-Jordan function, I delta, is a skew-symmetric and Hermitian. This means that it admits a spectral composition with pairs of positive and negative eigenvalues. And since the matrix has even rank. So there is a unique choice of its positive part. And we assign the meaning of vacuum of a Gaussian state to its positive part. So defining this Gaussian vacuum state as the positive part of the poly-Jordan, define a unique vacuum state even in curved backgrounds. Now, everything that I talk about is more in the operator perspective, but we also have a path integral description. And this path integral works through a double path integral approach, where we have two histories, and we also have a measure for our double path integral, which is known as the decoherence functional, which basically imposes causal and anti-causal orders on the function on our spacetime. And we can rewrite our decoherence functional in a similar way as in the continuum theory, where it can be written as an exponential of a bilinear, a quadratic function, which in the continuum usually we think about as the difference of the action of different histories. Now, I want to introduce you to the causal ordering operator, which is the analog of the time ordering in the continuum. So basically, given a product of fields, it just spits out the fields in a causally ordered way without adding the contribution from any commutation relations. And it's a really useful operator since it allows us to define a Feynman propagator, so the expectation value of the causally ordered products of two fields. So now I want to show you how in this free theory we can use our decoherence functional and just integrate our measure with for instance here the values of the functions at two different points, and I'm choosing one function to be on the anti-causal ordered history and the other one on the causally ordered one. And if I integrate to those objects, then what I get is just the White-One function, so the expectation value without any causal order. Now instead, if I introduce causal ordering, if I integrate both histories which are on the same branch, so on the order one, then the coherence functional takes care of the inherent order of the spacetime points, so that what I get is the Feynman propagator. Now, just briefly, I want to introduce to you how we define Heisenberg fields. In the continuum, we have this usual idea of having just squeezing the interacting field with two unitary operators. And what we do is that instead of having an integral over time, we have just a sum over spacetime points, and then we replace the time order with the causal order. Doing that, It means that our sum, an exponential of a sum, can be rewritten as a product of exponentials. And if we look at this really simple example, I can highlight to you some feature of our results. And in this case, we just have one interaction point, which is z, and I want to compute the expectation value, the two-point function. And what we notice is that the series terminates. With that, I mean that there are no higher order contribution. And this is true whenever the interaction region is finite. Another important point is that here I'm drawing an undirected edge as the Feynman propagator. And instead, with an arrow, I represent the retarded propagator. And in our Feynman rules, there is always a causal path from the internal vertices to the external ones. And another important point is that in this loop at z is the Feynman propagator in the coincidence limit, which, however, in our case, does not diverge, but it's just a finite number. The reason is because in our computation, we have a covariant natural UV cutoff that comes from how we built the theory, so that our Feynman propagator in the coincidence limit is completely finite. So I think I'm going to skip through some formalism, but what I want to mention is that we can define also generating functional, and from that we can just take the derivative of the generating functional in informalism and define some correlators, and we can also go forward and build an in-out formalism. And as well, we can also define scattering amplitude-less matrices. I don't want to go into the details because we will need to talk more about how the theory deals with asymptotic states, but I'm happy to take more questions if you are interested in that. So just to conclude, we can compute correlators on both flat and curved backgrounds. And this is really interesting because it would allow us to look for cosmological signatures of space-time discreteness. And we also use some techniques that can be useful to think about whenever instead we talk about a continuum QFT. For instance, we use a covariant regularization scheme, and in our case, there are no UV divergences given the setup. So thanks for listening, and if you have more questions, I'll be around for a few hours more.
Questions for Emma?
So I have a couple of questions. Yeah. So one thing is that you choose the Poisson distribution. So I mean what is the motivation behind choosing that particular Poisson distribution and not some other distribution? And the other thing is that as far as I understand, you already need the classical background solution, right? I mean, if I didn't know that certain geometry exists as a solution of Einstein equation, then I cannot distribute the points on it.
These are really good questions. Yeah, for the second one, what we are trying to study is given a set with a partial orders, can we have any topological invariants which tell us which kind of manifold we are looking at without doing the embedding? I showed you this procedure because this is something that it's useful in the QFT case where we want just to fix a background and be sure that the background is the same as the resembles and is embeddable in a continuum manifold. And but yeah, you're totally right that there is also the opposite question of in the picture of path integral over geometries, we are summing over different orders, like partial orders. And in that case, we would like that the path integral suppresses the causal sets which do not resemble a continuum manifold. So the idea would be, okay, let's study which topological feature which you can extract from posets, and the one which the topological features which resemble continuum manifolds are the one that we would like that the path integrals does not suppress. Yeah. And for the first question was about why Poisson distribution. And first of all, it's because it's covariant. While if we choose a lattice, for instance, and we boost our frame, what happens is that in the same region we would find a different number of points per unit area. While instead we would like to have that on average the number of points per unit area is constant, and this would ensure covariance. And with a Poisson distribution, we are minimizing the standard deviation. We could choose another distribution, but we choose the Poisson one because it's the one that is uniform and random.
Since you said this is an approach to quantum gravity, there's something that confuses me, which is that the whole idea seems to be very tied to having degrees of freedom tied to local points of space-time. However, in gravity, we know that's not the case. There are no local diff invariant operators. There are no local gauge invariant operators. You would see this even in the classical theory by virtue of the Gauss law.
Yeah.
So how do you accommodate for this fact? Because there is no notion of an operator that you can tie to each point in space-time.
We can smear our operator on different space-time points.
You would need to smear it over the whole Cauchy slice. You can't smear it on any bounded region to get a diff invariant operator.
We don't have a Cauchy slice notion.
But whatever in the continuum space-time would go off to infinity. All I mean to say is that you can't define a diff invariant operator in any sense of a bounded region. So you'd have to maybe sum over operators that kind of go off to whatever the notion of infinity is to get a diff invariant operator.
Yes, and also something that I haven't mentioned is that in this theory, if you look at a point and you look at the points which are at the same proper time, like in the continuum you define an hyperbola. So in this case, you would have like an infinite number of points at the same proper time. And so, yeah, if you want to define points which are like I'm not sure I can answer to your question, but yeah, I wanted to mention that this is another feature that might disagree with. Yeah.
Okay, I'll postpone the rest of this discussion in the interest of time. Let's thank Emma again.